Okay, in this video we're going to look at two more examples of finding volumes of solids of revolution using both the shell method and then the disc or washer method, wherever is appropriate, and then we can kind of compare which method might be a little bit easier. Okay, so in this particular problem number 2, we're going to find the volume of the solid bounded by y equals x squared, y equals 0, x equals 2, rotated about the y-axis, and first we'll use the shell method, shells, and then afterwards we'll use the disc or the washer method, whichever is appropriate. So first thing to do is to sketch the region. Okay. All right, so there is the region, and we are rotating this around the y-axis. If we're doing the shell method, your representative rectangles, which are going to be your shells you rotate around, they need to be parallel with the axis of revolution. So that means that they need to be up and down, and so they need to be functions of x, okay? So the distance from the center of your shell to the axis of revolution, your p of x is going to be equal to x, and then the height is simply the x squared. So for your shell method, volume is equal to 2 pi, integral from a to b, p of x, h of x, dx. So that's going to be 2 pi, integral, and we are doing in terms of x, so limits of integration for x are 0 to 2. X times x squared dx. It's going to be 2 pi, integral from 0 to 2 of x cubed dx. So it's going to be 2 pi, x to the 4th over 4, evaluated from 0 to 2. So it's going to be 2 pi times 2 to the 4th over 4. So that's going to be 16 over 4, which is 8. So we're going to get 16 over 4 is not 8. 16 over 4 is 4, pardon me. And then times 2 is 8 pi. And that's approximately 25.1327 units cubed. Okay. And this was just straightforward, easy with the shell method. We'll go ahead and look at what it would look like using the disc or the washer method, and it is possible that it might be a little bit more complicated. All right, so we're going to go ahead and sketch the same region here. Okay, rotate around the y-axis. Now, if you notice here, you have a big cavity or gap between the axis of revolution and the figure. So because of that, we're going to be using the washer method. Okay, so our inner radius, there's our, we're going to do our outer radius first. Here's your outer radius. Okay, so your outer radius is simply going to be 2, and it doesn't matter where you're at. So if you're up here, it's going to be 2 the whole time. Okay, the inner radius is going to be variable depending on where you're at. So if you're down here, it's going to be smaller. All right, so we got to figure out what your inner radius is. Now it's determined by the function y equals x squared. So y equals x squared is going to determine this distance. Okay, so we need to solve that for x to determine this distance. So if we solve that for x, we're going to get x is equal to plus and minus the square root of y. Okay, so we're in the quadrant 1, so we're going to be using the positive version. X is equal to square root of y, and that is going to describe this distance right here. That's the distance. Okay, now negative square root of y is going to be the left side of the parabola, and positive square root of y is going to be the right side of the parabola. So we're going to use the positive side of the parabola. That's going to be r of y is equal to the square root of y. That is our inner radius. So when we're doing the washer method, is volume is equal to pi, integral from c to d, big radius squared minus little radius is squared, and then integrate with respect to y, so pi. And then we're integrating with respect to y, so we need to look at limits of integration on the y-axis, so we're going to go 0 to 4. Okay, outer radius squared minus inner radius squared, so the outer radius is 2, the inner radius is the square root of y, so pi, integral from 0 to 4, 4 minus y dy. So pi 4y minus y squared over 2 evaluated from 0 to 4. So it's going to be pi, and then that's going to be 16 minus 8. So it's going to be 8 pi. Okay, and so we end up with the same value as the other one, and that's what we should. If we're not, then that means we've made an error somewhere. I would say that both the shell and the disk and the washer method, they're about the same level of difficulty. Maybe you could say that using the washer method was slightly more difficult. And so, it kind of depends on how easy it is to solve for one of the variables here. So we needed to solve in this problem for x, and so that was a little not terribly difficult. In the next example, we'll see where that might be a little bit more difficult, and so you might be wanting to do the shell method. Okay, so this next problem is going to be a little more complicated. So we're going to go ahead and speed it up. It says find the volume of the solid bounded by y equals 4x minus x squared, y equals 0, about the line x equals 5, and we're going to use both the shell and then whatever is appropriate between the disk and the washer method. Okay, so this thing has some complexities because of what we're rotating around, and then how we determine our distance from a representative rectangle to the axis of revolution. That's going to be can be a little bit tricky. All right, so we'll go ahead and get this ready to go. Okay, and I know it's a parabola. I know it's opening down, so I'm going to go ahead and plug in the integers from 0 to 4 into y equals 4x minus x squared to get the heights. So if you plug in 0, y is 0. Plug in x is 1. You got 4 minus 1 squared. That's going to be 3. Plug in 2, you have 8 minus 4, which is 4. Plug in 3, you have 12 minus 9, which is 3. And if you plug in 4, you have 16 minus 16, which is 0. So there is the parabola that we're looking at, okay? And then we'll go ahead and sketch the region, and then we're rotating it around the vertical line, x is equal to 5, okay? Now, if we're doing the shell method, our representative rectangles need to be parallel with the axis of revolution, so they're going to be up and down. So your functions are going to be in terms of x. So if your representative rectangles or your radii, they're going up and down, functions of x. If your representative rectangles are horizontal and your radii are going out horizontally, then that's going to be functions of y. Okay, so we're in functions of x. Okay, so the distance function, the representative rectangle to the axis of revolution, it's going to be a little bit trickier. So we're going to be integrating with respect to x, and our region goes from 0 to 4. So the volume is going to be 2 pi, integral a to b, p of x, h of x, dx. So that's going to be integral of 2 pi, integral from 0 to 4. Okay, so here's what we want to do. When we're all the way here, when x is equal to 0, let me use maybe a different color, so maybe let's use some orange. When we're all the way here at x equals 0, then the distance from here to the axis of revolution is 5, okay? All right, so when x is equal to 0, the distance to the axis of revolution is 5. Now, at the end of the limits of integration at 4, our distance from 4 to 5 is only 1. So when x is 4, the distance is going to be 1. And so we have a linear relationship between the x position and its distance from 5. So we can go ahead and find the slope, where it's going to be the change in distance, so 5 minus 1, over the change in x. So 0 minus 4, so it's going to give us negative 1. Now you can think of this as your y-intercept, or because we're using variable d as our output, this would be your d-intercept. And so we'd have y is equal to negative x plus 5. And that's going to appropriately describe the distance from the representative rectangle to the axis of revolution, depending on the x value. So that's exactly what we want. Okay, so it's going to be 5 minus x, or negative x plus 5, doesn't matter. So 5 minus x, okay, and then the height function's a little bit nicer. Height function is simply going to be the function itself, 4x minus x squared. And dx, okay, so that the hard part was coming up usually the hard part is coming up with that. Okay, and usually it's going to be something like wherever you're rotating around minus x will do that for you. Describe that distance. Okay, so we got 2 pi integral from 0 to 4 of 20x minus 5x squared minus 4x squared plus x cubed dx. And then we'll go ahead and combine our like terms. So 2 pi integral from 0 to 4 x cubed minus 9x squared plus 20x dx. And that's going to be 2 pi x to the fourth divided by 4 minus 3x cubed plus 10x squared. And then we're going to evaluate that from 0 to 4. So 2 pi, and that's going to be 64 minus 64 times 3 plus 160. So that's going to be 2 pi times 32, and that's going to be 64 pi, or approximately 201.0619 units cubed. Okay, so it's a little bit trickier because we're not rotating around the x or the y axis, and it's got that a little bit tricky distance function. Okay, now we're going to see what this thing looks like if we're going to try to do the disk or the washer method, and it's going to be a mess. Okay, out of the two options, the shell method is going to be easier, and because your function here, you're going to need to solve this for x, and that's going to be a little bit difficult. All right, so we're going to go ahead and figure out if we're going to use the disk or the washer method. Okay, and we're going to just resketch our region that we're going to rotate. So there it is, and the axis of revolution is x equals 5. Okay, all right, so whoops. Notice that we got a big old cavity right here between the figure and the axis of revolution, so this is going to be a washer method. Our function is y equals 4x minus x squared. So we got to talk about an outer radius and an inner radius, okay? And those are going horizontal, so we need things in terms of y. So we do need to solve y equals 4x minus x squared in terms of x. So we're going to complete the square. Now, to complete the square is easier if your x squared is positive. So we're going to go ahead and multiply by -1. So negative y is equal to x squared minus 4x. Your linear coefficient is -4. Divide that by 2, and that's -2, and square that. So what we're going to do is we're going to add 4 to both sides. So 4 minus y equals x squared minus 4x plus 4. Now doing that, we have a perfect square on the right-hand side, which is x minus 2 quantity squared. Take the square root, don't forget your plus or minus, and you get x minus 2 is equal to plus and minus the square root of 4 minus y. Add 2 to both sides, and you have 2 plus or minus the square root of 4 minus y is equal to x. So you can see that this is a mess, and so if we were given the option of only having to do disk, washer, or the shell method, we'd want to do the shell method. All right, so we have two different functions, and they're going to describe two different sides of the parabola here, okay? And so we're going to have a left side and a right side. And we're going to pick some points for the y to kind of figure out where the x is going to be, kind of see if we can follow a pattern here. All right, so let's look at x equals 2 minus the square root of 4 minus y. And I'm just going to pick some values for y, so I'm going to look at y equals 0. So if y is equal to 0, then you have 2 minus the square root of 4 minus 0, so that's going to be 2 minus 2, so the x is going to be 0, and so that places us there. Okay, and then I'm going to pick a number that's going to be nice here for the y, so I'm going to pick 3, so then I have 4 minus 3, which is 1. Square root of 1 is 1. All right, so y is equal to 3, then you're going to have x is equal to 2 minus the square root of 4 minus 3, so that's going to be 2 minus 1, which is 1, so that gives us the next point. And so that's describing the left side here. Now, the highest the y gets is 4, so if we do y is equal to 4, then we have x is equal to 2 minus the square root of 4 minus 4, so that's going to be x equals 2 minus 0, so x is equal to 2. Okay, And so that describes the left side of the parabola there pretty nicely. Okay, and so our outer radius coming from the axis of revolution, which is x equals 5, hits the outer edge of the figure right there. Okay, all right, so the outer radius is going to be a little tricky. Okay, so you see this right here? That's what x equals 2 minus the square root of 4 minus y describes. It describes the area, not the area, it describes the distance from the y-axis to the sideways parabola here. So that's what makes this a little tricky. Okay, so that is x equals 2 minus the square root of 4 minus y. All right, so that describes this distance. We want to count this distance, okay? So if we do 5 and then minus this little piece here, that's going to describe our outer radius. So 5 minus 2 minus the square root of 4 minus y is going to be our outer radius. So it's going to be 3 plus the square root of 4 minus y. Okay? All right, now we're going to make sure that the 2 plus the square root of 4 minus y describes the right-hand side of this parabola. So x is equal to 2 plus square root of 4 minus y. And then we'll go ahead and we'll start with y equals 0. So y equals, I did it backwards. We're going to start with y equals 4. So you have 2 plus the square root of 4 minus 4. So it's going to be just 2. Okay. So that starts us up at the vertex of the parabola. Now we're going to look at y is equal to 3. So we'll have x is equal to 3 because we have 2 plus the square root of 4 minus 3. So that's going to be 2 plus the square root of 1. So that's just 2 plus 1, which is 3. So you see we have the next point here. And then we're going to do y equals 0. So I'm picking these specific values of y because they play nice with the radical. So y equals 0, then we have x is equal to 2 plus the square root of 4 minus 0, so it's going to be 2 plus 2, which is 4, which gives us that last point here. And then we can kind of see that this x equals 2 plus the square root of 4 minus y describes the right-hand side of the parabola. Okay, so x equals 2 plus the square root of 4 minus y, that is going to describe the distance from the y-axis to the parabola, the right-hand side of the parabola. Okay, what we want to count for the inner radius is just this piece right here. So if we do 5, which is the whole distance here, and then subtract this portion here, then we'll have described the inner radius. Okay, so the inner radius is going to be 5. So again, here I'm labeling it. 5 minus 2 plus the square root of 4 minus y. And so that's going to be 3 minus the square root of 4 minus y. And so obviously this is the much more difficult one because of the functions, the complete and the square. We actually have two different functions. This is a washer method. And both the outer and the radius, outer and inner radius are a little bit complicated to come up with. Okay, so volume is pi, integral from c to d. Big radius squared minus little radius squared, and integrate with respect to y. So it's going to be pi, integral from 0 to 4. We're doing the y-axis. 3 plus 4 minus y squared minus 3 minus 4 minus y under the square root squared dy. Okay, and we're going to go ahead and work that out on the next page. So go ahead and speed that up. So there it is. Pi, integral from 0 to 4. Go ahead and FOIL. So 3 times 3 is 9. 3 times the square root, and then the square root times 3 will give 6 of those square roots. The square root times the square root will free the 4 minus y. FOIL out the other part. So 3 times 3 is 9. 3 times the negative square root, and then the negative square root times 3 is going to give us a negative 6 square root of 4 minus y. Again, we're just FOILing. Negative square root times the negative square root is going to be positive, and then the 4 minus y is now free. Okay, so this becomes the integral from pi, and then the integral 0 to 4. 9 minus 9 is gone, 6 square roots of 4 minus y minus negative 6 square roots of 4 minus y is going to give us 12 square roots of 4 minus y. Okay, and then we have 4 minus y minus the quantity 4 minus y, so those absorb. And so we're just going to integrate that with respect to y. This is a good candidate for u substitution. U is 4 minus y. Du is negative dy. Solve for dy, and we have negative du is dy. Because this is a definite integral, we can also convert our limits. So our lower limit is y equals 0. The relationship between u and y is u equals 4 minus y. So u is going to be equal to 4 minus 0, which is 4. The upper limit is y equals 4. So u is equal to 4 minus 4, which is 0. So we have pi, integral from 4 to 0, 12 u to the 1/2, okay, and then dy is negative du. So when we integrate that, that's going to be negative 12 pi u to the 3/2 divided by 3/2 evaluated from 4 to 0. Okay, so that's going to be 8 pi u to the 3/2 evaluated from 4 to 0. So negative 8 pi times the quantity 0 to the 3/2 minus 4 to the 3/2. It's going to be negative 8 pi times negative 8. And so there we go. We got that 64 pi, and that's what we got using the shell method, but we did have to work at this a little bit more. So 201.0619 units cubed. Okay. Alrighty, so that's it for this one. We have one more video, and I think that one has one more example integrating with respect to x and y. So we're going to see both the shell and the disk or the washer method, whatever's appropriate. Alrighty, we'll see you next time.